Okay, guys, I'm Pritam again. So welcome to the class of Step-Growth Polymerization. So I hope that you're having an amazing day. I think the great weather. And is by far is one of the easiest part to learn in polymer chemistry step-growth because it's really easy. There is not much thing to understand. You have to just know the examples. But still, the application is so important, like the crazy application. So that is why I think it's really, really interesting. So I think it's really great to learn step-growth polymerizations today. Okay, so these are some of the questions that I am going to go through one by one, like the prerequisites of the monomer that you need for SGPs. Some typical examples for SGPs, including their chemical structures and the main applications. The major differences between the SGPs and chain growth polymerizations. What are the various methods of producing polyethylene terephthalate and which route is typically preferred in the industry? What are the preferred conditions for achieving high yields in SGP? And finally, we are going to see the Flory's equation to understand the kinetics of the step-growth polymer. So this is, I think, the last question. Probably this is something you need to understand a little bit. And the rest of the questions is something you need to know. These are various examples. You just have to know. And what I'm going to do is to find out the key points that you need to remember so that it can be easy for you to apply in the real world or even to remember for yourself. Okay, so the first question, what is the prerequisite that we need for step-growth polymerizations? So first of all, you need a functional group which must have a bifunctionality. So it really makes sense, right? You just take a normal reactive group which has only one single functionality. They just react with each other and the reaction finished. But if you would like to continue this reaction, you need to have another functional group on the other end of the chains. That's why they can continue the reaction. So this is completely no-brainer that you need a bifunctionality at least to continue it towards polymerizations. Secondly, the two functional group that you are choosing, they has to be sufficiently reactive so that you don't have to put any kind of initiator. So that is one of the striking difference with the chain growth. In the chain growth, they are not that reactive. That's why you need to add an initiator in order to start the reactions. But in this case, you don't need any initiator. You just have to put some temperature, high temperature and high pressure. And that's why this is enough in order to start the reactions. Yeah.
Sorry.
Yeah. So you just have to increase the temperature or pressure, and that is actually enough to start the reactions between the monomers that you have chosen, right? So in the process, you are also removing some small groups, small group in a sense like water, usually water or alcohol. Sometimes there are other byproducts. And this is really important to remove those byproducts in order to drive the equilibrium towards the product side. So I'm going to explain these things in a detail in the next few slides. But this is some of the prerequisites that you need to understand, which are really simpler way to do a reaction like A plus B is equal to C, right? And of course, then you have the polymer, which is completely like a stepwise manner, like two monomer is reacting together, making a dimer, then two dimers is reacting together to making a tetramer, and then oligomer, and then so on, and making the polymer. So it's really like a reaction A plus B, and which is creating a C. Like the same step is really repeating every time. So here, one of the example that you can create a polymer which is called polyethylene terephthalate, and the monomer usually is ethylene glycol, where you have a two alcoholic group, which is representing here, let's say A, and then you have a dicarboxylic acid group, which is representing here the BB, just to give you the example of this kind of step-growth polymer. And in the process, you are also releasing water, so you have to remove the water in order to drive the equilibrium towards the product side. So here I just would like to show you one of the typical example of a polyesterifications. By taking a monomer, which is ethylene glycol and oxalic acid, right? So just to tell you what is the difference with chain growth polymer that you have studied before. So for example, here you take 8 molecules of dialcohol and 8 molecules of diacid. The first reaction, it is going to be like A plus B is equal to C. So this is going to react with this, producing this. So each of them are going to react with each other, and they're going to produce this. So notice one thing. On the first reaction, all the monomer just finished. All of them is finished. And then they are going to again react with each other. So it's again the same fashion, like A plus B is equal to C. One of the things you have to also notice here, at the beginning, you have no degree of polymerization, 0 degree of polymerization, but you have the highest number of functional group. More you do the polymerizations, more you are going to reduce the functionality. So here it was 16, here it was 8, and then here the degree of polymerization increased from 2 to 4, but you have the half of the functional group present from the before. So this is one of the striking difference that you have from chain growth polymer, that you are always losing the functionality in the unit chain. And that is the reason why the kinetics of step-growth polymer is so slow. And I'm going to explain, and I'm going to bring back this slide in the kinetics, so I'm going to explain it to you. Any questions here in these examples? Okay. So now we are going to see some of the examples of SGPs, including their chemical structures and the main applications. So before I show you the examples one by one, just to show you the list of step-growth polymer which are usually available. So here you really have to just remember what are the main step-growth polymer which are available, like polyester, polyamide, epoxy resin, polyurethane, polyurea, polyether, polyamide. At the beginning, it maybe sounds a little bit daunting, but if you just see the name, how they came. So polyester, why it is called polyester? Because in the repeat unit, you have an ester group. So this is called ester group, and now you are repeating the ester group. That's why it's called polyester. It's the same in case of amide. This is called amide, and you have the polyamide. That's why it's called polyamide. It's the same for urea, same for ether. Now you have to just remember how a ester form. A ester usually formed by a reaction with alcohol and acid. Amide usually formed by a reaction with amine and alcohol. This is the only thing you have to remember. So first you have to remember the 6 or 5 example of step-growth polymers that you have, and why they're called, because you are creating this particular linkages in the repeat unit. And then you have to just know how you can create these ester linkages or amide linkages or the urethane linkages, right? So if you are talking about the bifunctional group, in case of step-growth polymer, you are also releasing some of the small groups. For example, usually in case of polyester, you are releasing water as a small group. In case of amide, also again water. It can be also alcohol, depending upon the monomer that you are choosing. In case of polyurethane, you are releasing alcohol. So these are the small groups you are actually releasing in the reactions. So this is the only thing you have to understand here. And then these are the trade names that you have to remember. So these are the trade names which are taken by the that corresponding industry who created this polymer in their own process, even though they are using the same monomer. But of course, they have some secret recipe of creating this polymer. So that's why they have different name, which is the registered trademark of the name. And they have like one of the best application which is available in the real world. So even though the reaction itself is really easy to understand, you have like 4 or 5 combination like amine and alcohol or acid. By just combining each other, you are creating this polymer. But the real life application is like crazy. That is why it is so important. So when you are choosing the monomer, you have to notice like you have like 4 or 5 combinations like alcohol or acid or amine, and then you are choosing like combining 2 monomer which has like electrophilicity and nucleophilicity. So it's a kind of give and take relationship between them. Like the acid, it is hungry for electrons, so it really like to have more and more electrons. It has a lack of electrons. On the other hand, the alcohol, it has a lot of electrons. So that is why they can react with each other, and that is why they are reactive for each other. So if you just add 2 alcohol, which is happened here, in this case, you have to increase the temperature. But in this case, they are already reactive each other because they are actually making themselves reactive for each other. That is why you don't have to put so much energy like temperature or pressure. right? Okay. You have any question here? Okay. Okay, so now we are going to see some of the examples one by one. So for example, polyester. So one of the polyester which is really, really famous called polyethylene terephthalate, in short PET. So here I just wanted to show you in the monomer how the reaction has been started. So you take dimethylene terephthalate and then you take ethylene glycol. Usually again the electron give and take policy is happening here. It has a abundance of electron, it has a lack of electrons, it is giving the electron attacking in this carbonyl group, and then it is releasing this OMe group, which is in terms making the methanol, right? So these are some of the trade name of this polymer, depending upon which company has been registered according to their name. And of course, it has a lot of good application, very high density, high strength application like food packaging or electrical insulations. Dacron, which is very popular, like used in a textile industry, surgical suture, or like sail clothing industries. There is another example which is called, polyester, which is called PCT. The name is that long name, as you can see here, polycyclohexamethylene dimethylene terephthalate. So in this case, what you are doing, you are just replacing this aliphatic group with a cyclohexane group. And of course, as you are replacing this monomer, the end product, the polymer that you are having, of course, it will have some different properties. Even though it's a really high tensile polymer, but it will, of course, have some different properties. And you are creating the codel, which, of course, used for some different type of industrial application like active sportswear or home textiles industries. So bear in mind that in online, the information that is given to you, it is written here polyethylene terephthalate. It's not polyethylene terephthalate. The actual name is PCT. So if you want to remember the name, just see one thing, how they are actually giving the name. For example, if it is called polyethylene terephthalate, in the repeat unit, you have a ethylene group and you have a terephthalate group, polyethylene terephthalate. Here it is called polycyclohexamethylene terephthalate. So in the repeat unit, you have this cyclomethylene group and you have terephthalate, and that's how you're just making polyethylene terephthalate. That's simple as it is, right? You just have to know which monomer are inside the repeat unit, and you are just putting a poly in front of it. That's all. Okay. So another example of polyester is a polycarbonate. Again, why it is polycarbonate? Because you are creating a repeat of carbonate group in the polymer. So here in this case, you are taking bisphenol A and diphenyl carbonate, and you are releasing a phenol. So not always you are releasing water or methanol as a byproduct. You can also release such big or bulky group like phenol. And of course, it is also going to be useful when they are going to extract it from the reaction. So the industrial applications, which is called Lexan, and you can use it for bulletproof glass, which is really exciting. Also useful for signage display, aerospace and defense industry, construction materials. So you may think, wow, this is so strong that you can use it inside a bulletproof glass. But if you understand how a bulletproof glass actually manufactured, then you will understand that actually this is not the material which is stopping the bullet, right? I don't know if you want to interested to know how bulletproof glass is happening. If I just going to explain it very shortly, in case of bulletproof glass, what they do, they actually make several layers of glass. So the glass which is actually stopping the bullet is actually the glass, not the polycarbonate or the plastic. So what they take a very high strength glass, which has a very high resistance of absorbing energy, and then they stack up all those glass together. And what polycarbonate is useful here, they just put some sheet of polycarbonate in between the glass slide. So polycarbonate is really transparent, first of all. And secondly, what polycarbonate is doing actually in this bulletproof glass is actually absorbing the force of the projectile and is dissipating all over the surface. So just imagine that you are shooting a bullet in a window, and then you have a very high projectile force from the bullet, and it is only acting in a really small surface area. So the force by the area is so high, it's just penetrating through like a piece of cake. But if you have a bulletproof glass where you have a polycarbonate in between them, So it's really absorbing the energy, and it is dissipating the energy towards the glass. So you might have saw in the movies when they're shooting on the bulletproof car, you'll see the crack all over the surface. So that is why the polycarbonate is actually absorbing the energy and is dissipating all over the surface. So now you have the force by the area is so high that it is overall is forced by area so less, right? That's how the principle of bulletproof glass works. Okay, I was just interested in this thing, that's why I just take time to explain it. Okay, so there is another class of step-growth polymers which are also very, very popular, which is called polyamides. So, of course, you may have heard about this name, nylon, which is quite popular. It's one of the revolutionary material, the first synthesized by carothers, and then all the step-growth polymer that I saw, which came afterwards, after this discovery, and it's just changed the world, to be honest. So you can create nylon, one of the monomer that you can take like either 6-aminohexanoic acid, or you can take a ring of caprolactam. And then here you will see that the two different functional groups, they can be present in the same chain. And then they can just react with each other, and they can produce this nylon. You can also produce it by taking two different monomer, which is just taking the functional group completely separate from each other. So you have adipic acid, which is only containing carboxylic acid group. You have hexamethylene diamine, which is only containing amine group. And then you are just reacting with each other. And in this case, usually the reaction is done in an interfacial polymerization. And if you ask me why, then usually these two monomer, they doesn't have the same solubility. So this one is soluble in aqueous solvent. This one is soluble in an organic solvent. And that's why you have to make them soluble in two different solvents, and then you have to stack up on each other. And the interface between the aqueous and the organic solvent, they come close to each other, and then they can create the polymer. So in order to continue the reaction, in order to continue the product, you have to remove the product from there, so that further solution of organic layer and aqueous layer, they can come close to each other and they can continue the reactions. So this is one of the characteristic of an interfacial polymerization. You have to always remove the polymer from the system in order to continue the reaction. Now I have one question for you. Can you tell me why if you see the structure here, it's basically the same structure. Exactly the same structure here, here, and here, right? But why it is called nylon 6, but in this case it is called nylon 6,6? Can somebody try? Just to give you a hint, think about the repeat unit. All the nomenclature is coming from the repeat unit. You can try? Just say anything.
Amine is at the first one and the sixth one, and then continues. That's why sixth one.
Sorry,
In the repeating unit, there's two amine groups, whereas not amine with the nitrogen.
Yeah, you are very close.
And in the above ones, there's only one.
Yeah, you were really close, really close. Somebody want to try one more time? So, very simple as it. If you see in the nylon 6, you have, what is the 6 representing here? Did you find anything which is 6?
Carbon.
Exactly. In this case, how many carbons you have? 12 carbon, but this 12 carbon is coming 6 is coming from here, 6 is coming from here. So it's just to differentiate when you have the product. When you say I have a nylon 6,6, it will directly strike in your mind, oh, nylon 6, that means it is coming from these two combination of monomer. It can be nylon 6,12. So if it is nylon 6,12, then it is this 6, and there is a 12 carbon here, or nylon 6,8. It's just like this, just to understand what is the monomer, because depending upon the monomer you are choosing, even though they have the same repeat unit, they have a different properties. So once you know the name, you also know what is the property. So that is the only reason why they make this nomenclature like that. Great. So of course, you know the application of nylon. Of course, it is used for swimwear, fishing lines, swing thread, motor engine, electrical wires, and plenty of other examples. I think we are using nylon in our everyday daily use. So these are some of the examples that you have to remember. then there is coming polyaramides. So in case of polyaramides, the similarity between the previous example is exactly the amine group, but why it is called aramide? Because it is a aromatic amine. So you are using, instead of using the aliphatic group in case of nylon, you are using a benzene ring, which is an aromatic ring, and you are creating these amine linkages. So aromatic, amine, aramide, right? And what you are creating is Kevlar. Kevlar is one of the strongest polymer ever created by the man in history. Why? You are using Kevlar for bulletproof vest. It's so strong that it's much more stronger than metal like steel or iron, but at the same time, it's way more lighter than metal and iron. So that is the reason they use Kevlar in a warfare items like polymer vest or like a helmet or something like this. Even it can also use in a tire. So before invention of Kevlar, in order to increase the strength of tire, they need to use some metallic thread, right? But the problem with metallic thread is that they're also getting damaged by oxidation, and also they are not flexible. So once they find Kevlar, which is even stronger, but at the same time they're also flexible, they replace suddenly from metallic thread to Kevlar in a tire. So this is one of the strongest man-made polymer ever built. There are also some other applications like in canoe or in a speedboat, like in a racing speedboat or panel wings of Eurofighters. You can also use it for as a Kevlar. The main reason is super strong material. At the same time, it's super flexible and also very lightweight. So now the question is why Kevlar is so strong, or why it has a so high modulus or elasticity or chemical resistance. The reason behind is mainly two, because as you are using, instead of using aliphatic chains, in case of nylon, which is making it a little bit more flexible, you are using a rigid aromatic ring. So due to this rigidity, first of all, it is making the chains of the polymer highly organized, number one. And number two is that you are also creating very strong intermolecular attraction forces. So as a result, for these two reasons, the chains of the polymer, they are highly compact with each other. And that is why the strength of the Kevlar is on par. Like there is nothing on more than that. So that is the reason why Kevlar is so strong. Do you have any question? Anything to know here? Right. Okay. So the next example we like to discuss about the epoxy resin. So before I directly show you the industrial example, I just want to show you a kind of reaction mechanism. What is the main reaction mechanism is follow. So in case of ring opening polymerizations under SGP, the reaction is usually go like this. You take the epoxy ring, and then it needs something to open the ring. So in case of CGP, usually you use either H+, like like acid catalyst, or like a base, which open the ring. In this particular case, you use amine, which actually act as a hardener or like a curing agent, right? So it react here, open the chain. It still have one reacting site left, and then it again react with another chain, and then it's create this. So, and the reaction finish here, which is completely striking than the CGP. I'm going to show you the difference with CGPs. This reaction can be also done autocatalytically. For example, when you create this OH group also going to influence this oxygen, and it will tell it to go further reaction. So it will go even faster reaction due to its autocatalytic activity. So if you see the same ring opening polymerization that we have studied in case of CGP, you see it's completely different in this case. So in this case, usually you start with a catalyst, either it's an acid catalyzed or as a base catalyzed reaction. Here, acid catalyzed, base catalyzed. And then it will start first, this catalyst initiate the reaction, and then after that you have a charge at the end of the chain, and this charge is actually carried forward to add more and more monomer. So you are going to add more and more monomer as long as you have monomer in the system. So in this case, the reaction just stop here. In this case, it will continue the reaction. This is the main difference of ring opening polymerizations of under SGP and under CGP. right? Okay, can I go next slide? So this is one of the industrial example which is already have been taken by Sam in the PowerPoint. So you are taking a epichlorohydrin and then you are using bisphenol A, and I just try to here show you how they are reacting with each other. So this bisphenol A, they can react in two different sides in two different ways. So it can react in this carbon, it can react also in this carbon, and you are making this pre-polymer structure. And then once you have this pre-polymer, then you have a choice to add a hardener. Usually the hardener are like diamine, and what it does, it takes this pre-polymer, is just join this pre-polymer, making a kind of epoxy resin structure. So it's actually act as a curing agent. And now you are wondering why you suddenly want to add this and making this. So this is mainly for the industrial application. So here particularly this example is an example of a glue or adhesive that you use in an industrial application. You might have noticed one thing when you are, so one of the, first of all, show you the name of the product, Araldite. Araldite, I think you already heard about this name. So when you buy a pack of Araldite, you will see there is two tubes are there, right? When you want to use it, you have to mix the two tubes together, and then you are going to use it as a glue. So what happened, in one of the tube, it's containing this pre-polymer, and another tube is containing this hardener. So as long as they are separated by the tubes, they are not making any reactions. Once you need it for the adhesive properties, you just mix them together, and then they start this curing process, and then they stiffen up, and then they act as adhesive. That's the only principle of adhesive, right? Okay, here's one of the examples that I already tell you about polyamide. So here you have to just understand the main functional groups. Again, it's a diamine, as a dianhydride, is the name is here, and you are creating another industrial polymer which is called Kapton. And of course, it has really different applications. Usually it is used for PCB board, even for FFC board, insulation of spacecraft wearing or thermal blankets. So these are the applications you have to remember. Okay, and the last example is the polyurethanes, and I think you also know this when you are cleaning your utensils, which is like a scrubbing agent, like Lycra or like spandex, the foams that you are use. So usually it is created by this combination of monomer, and here the functional group that you have to remember is the diisocyanate here and the dialcohol. Okay, so we are going to finish the examples of the different step-growth polymers and their applications, and then we are going to move on to the next question. Before I move on, do you have anything to ask here?
When you talk about the epoxy resins and kind of making like the hardening part, when you add in your hardener, so one thing that Sam talked about is like how if you have smaller molecules that don't react to, like say you have too much of the hardener, too much of the pre-polymer, does that affect the properties if they're out of balance?
Oh yeah, surely. I think in the industry they have a separate section of R&D, and then they find out by changing the ratios. Of course, the ratios of the pre-polymer and the hardener affect. Like if you are, for example, I never worked in the adhesive industry before, but what I can tell you with a common sense, like if you are using less hardener, it will take longer time to harden up. If you are using more hardener, it will be hardening faster.
Okay.
So that's what I can guess. Okay. So the next question will be, what are the typical differences between SGPs and CGPs? Of course, there is a striking difference between SGPs and CGPs. So here I try to organize the differences from the beginning to the end. Like first of all, the choice of monomer that you will need for SGP and CGP. How, when you are going to do the reaction, what is the initiation step? What is the reaction mechanisms when you are following it? The reaction rate, the molecular weight that you are getting at the end, and the termination point. So these are some things which are, I think you're already aware about it. Monomer, of course, in case of SGP, you need a bifunctional monomer in order to carry forward the reactions. In case of chain growth, it's a monofunctional group. Usually, it is the unsaturated carbon that you are using, if you remember SGP before. In case of initiation, the bifunctional group, they are sufficiently reactive that you don't need any initiator. You just have to increase the temperature or the pressure, and they can start the reactions. In case of chain growth, you need to add in some kind of initiator like radicals or like catalyst in order to start the reactions. Their mechanism usually is between different functional group and is the same step over and over you are following. Whereas in case of CGP, you are just adding the monomer one by one to the same chain in a growing chains. So you can understand the reaction rate is slower. I'm going to explain this why it is slower when I'm going to explain in the kinetics. But usually, you can understand the same reaction is happening all the time in case of SGP. But at the same time, they're also increasing in polymer. So finding the probability of the two functional group will be also increase over time, right? So I'm going to explain these things in the kinetics, and I'm going to tell you in details why in case of SGP, the reaction rate is much slower. In case of CGP, it's much faster because you are just adding the monomer in the same chain. So at the end of the chain, you have the functional group, which is ready to react with the monomers, and there is plenty of monomers around. So finding each other is much easier in this case. But in case of SGP, they have to find the same different functional group, which is already maybe somewhere else, already entangled in a long polymer chains. It's much more difficult. That's why it's much more slower. And that is the reason also the molecular weight in case of SGP is usually not so narrow. It's much more broad distribution. Whereas in case of CGP, it's much more narrow weight distribution, and you can, because you have more control over the reaction, so that's why you can have much more predicted molecular weight in case of CGP. And the termination, if you visualize, in case of termination, you still have the reactive group at the end of the reaction. In case of CGP, the termination end, unless it is a anionic polymerization where it is a living polymerization. But again, after time, it is also neutralized with the atmospheric oxygen and moisture, right? Before I move on to the next question, anything you have to ask? Yeah, so these are not so much brainstorming thing. You have to just understand and you have to just remember. So what are the various methods of producing polyethylene terephthalate and which route usually is preferred? So first of all, polyethylene terephthalate is a highly useful and high demanding polymer. So that is why we are dealing with this question, and that is why we need to know what are the various process which is available in the industry. So these are the process which is already pointed out by Sam, like 4 or 5 steps, which is basically is just the different type of monomer depending upon their reactivity and their cost, and you are getting the same polymer. And here we are going to talk about mainly about the first 3, ABC, because those are the mainly used in the past in the industry. So if I just tell you in one word, so first of all, reaction A, which is the preferred choice, which is used in the industry nowadays. And the reason why, the main thing in one word is the cost. So industries only think about their cost. So that's why they make profit, right? So the overall cost of reaction A is the cheapest to produce compared to reaction B. In case of reaction B, you have previously it was followed because this monomer was the cheapest, but now they find another monomer, which is this. Now it is the cheaper than this. That's why they're following this. And the overall cost of this reaction is way more cheaper than this one. What about this reaction? In this reaction is much more faster. So faster is also can be useful. It can be as an advantage. But at the same time, as it is more reactive, it is also more costly. So they did a kind of cost-benefit analysis, and they find out that it's much more easier to use this cheaper monomer and do the reaction and to get the same product instead of using much more costlier monomer. So that is the main reason why reaction A is preferred compared to reaction B. And of course, in reaction C, they has to go for interfacial polymerizations because these two have a different solubility. So what happened that in case of interfacial polymer, you are usually making a polymer which is more fluffier. Then you have to go for more post-processing, which is also increasing the cost, because more you include steps, more it will increase the cost of the overall process, right? So that is also one of the reasons they don't really follow. But of course, some of the cases you may need particularly that properties of the polymer, and you may need to use more money to produce this polymer. So it is not completely discarded. It is also used depending upon your demand. Okay. So what are the preferred conditions to achieve high yields in SGP? It's a really interesting question. So before I go directly to the example of the preferred choices to get the higher yield, I like to explain you a little bit about Le Chatelier principle. I don't know if you know about this thing, but it's a really useful tool actually, which can not only be used for predicting SGP, but also can be useful for any type of reactions. So if you know the main principle, and then you can understand, you can apply it anywhere, not only in SGP, but also in CGP or any kind of normal reaction, radical reactions, or any kind of reactions. So Le Chatelier principle is saying that disturbing a system at dynamic equilibrium shifts the equilibrium in direction that counteracts the change. So in a simple word, you have some condition when you are doing the reactions, and you are just changing those conditions in order to manipulate the equilibrium. You are manipulating the equilibrium. Why? In order to gain some advantage towards product. Of course, you are doing the reaction to gain the product, right? So you are just manipulating the equilibrium so that you can have more product. So let's say one of the example, if I just take here in case of SGP, you take two different monomer, and then you get a polymer here, and in the process you also release some of the small molecule or byproducts, and also you absorb some heat, right? I just take the example of SGP, so then it can be more understandable to apply it in case of when you are going to discuss about SGP. Now, in this reaction, they have like three main conditions that you are using. First of all is the concentration of the reactant that you are using, the temperature of the reaction that you're using, and the pressure of the reaction you are using, right? So let's say you start this reaction with a particular known concentration, so the concentration you know. The temperature, let's say room temperature, let's say 25 degrees centigrade room temperature, and also you apply room atmospheric pressure, like normal atmospheric pressure. Now, you have these tools, and you can change those tools to manipulate the equilibrium. How? If I talk about only concentration, in this case, if you increase the concentration of the reactant in order to make this equilibrium again stabilize from the previous condition, the excess reactant is going to make some more product. So the equilibrium is going to shift toward the product if you increase the reactant, right? Just oppositely, if you have more product, so it will try to shift the equilibrium towards the reactant side. So of course you are not going to add some more product, you are actually creating product. So in this case you have to think in a way that you are decreasing the product. Decreasing the product, one of the example is interfacial polymerizations. So in case of interfacial polymerization, you are actually removing the product. So if you remove the product from here, it's also shift the equilibrium from the left to the right side, right? So this is the way you can manipulate the concentration in order to gain more advantage as a product. Okay. In case of temperature, you have to understand in the reaction, it is releasing heat or it is absorbing heat. So if it is absorbing heat, it's usually an endothermic reaction. If it is releasing heat, it is an exothermic reaction. So endothermic reaction, for example, when you are adding salt in water, and you may have noticed that the glass that you're holding is become cold. Why? Because it's actually absorbing heat. This is one of the endothermic reaction that we saw in our daily life. Example of an exothermic reaction is a nuclear fission, or like the atomic bomb. That is the reason why it is so much destructive, and it creates so much energy that it can destroy even a city. So this is just an extreme example that I just gave you. But how you can manipulate, let's say in this example, you are absorbing heat. So if you add more temperature in the system, in order to cope with that excess temperature, what the equilibrium will do, they will just react some more monomer and create some more product, and then try to minimize the excess heat if it is an endothermic reaction. In case of pressure, usually it works like if you add more pressure, it will favor the reaction towards the fewer molecule. For example, if you are adding like A plus B is equal to C, so you have more molecule here and you have fewer molecule here. So in this particular case, if you add more pressure, it will drive the equilibrium towards the product side, right? So it's opposite is the if you decrease the pressure. So if you decrease the pressure, it will drive the equilibrium towards the reactant side. Of course, you don't want, you are doing the reaction to have more product. Now, if you are going to apply this, so this is just a tool. It's not like a principle. It's just a tool that you can apply in order to gain some advantage as a product. So let's say you want to have more of this product. Can you tell me how you are going to manipulate this concentration of the reactant so that you can have more product? You have to increase or you have to decrease the reactant? Increase, right? Yeah. So if you want to drive the reaction towards the product, of course, you have to increase the reactant, so the excess reactant will react and they will prepare some more product. In case of product also, you have to decrease the product, as I explained. So either you have a choice, either you can remove the product or you can also remove the small molecule. Like this is a byproduct, but still it's a product, right? So you can also remove the small molecule, and this can also drive the reaction towards the product side. So that is the reason why in case of SGP, they need to remove the molecule. Of course, there is another reason, because if you keep the small molecule, it is going to react with this prepared polymer and make some side product. That is also one of the reasons. But removing the small molecule is also going to help you to drive the reaction towards the product side. In case of temperature, in this particular example, can you tell me, do I need to increase the temperature or need to decrease the temperature to drive the reaction towards the product? Yeah, because here it's in a room temperature, it's already an endothermic reaction. So what I need to do in order to get more product, you have to just increase the temperature and I have more product. And in case of pressure? Yeah. Again, as you can see here, you have more molecules. You have small molecules. So if you increase the pressure, then in order to cope with the excess pressure, it has to go to the smaller, fewer molecules, because small molecules, they take less surface area, so they have less pressure. More molecules take more surface area, they have more pressure, right? Okay, so now you understand the last layer. Yeah.
For the pressure part, if you have gaseous products, surely they have a better effect on the pressure.
Exactly. I didn't really tell you, but you actually get the point. So the pressure is more effective if you have a gaseous product, right? So if you have a gaseous product, the pressure is going to react much faster, and the pressure is going to be applied on them more efficiently rather than a liquid or a solid product. You're right. Okay. So now we understand the main tool. Yeah.
Sorry.
Yeah, no problem. Yeah. Go ahead.
That one. Like according to the principle, let's say you have one gaseous product, but you have how to explain it? How do you understand which effect is better? If you have fewer molecules or a gaseous product, where will it shift?
Yeah, I think
I'm making sense.
I think I understand. No, you're making complete sense, to be honest. What you want to say, like, you have one gaseous reactant and one liquid reactant, right? And
so let's say it's the same. So no, you have favors. I'm gonna think about it.
I get your question, to be honest. I mean, what you trying to ask me is, let's say you have this monomer, which is a gas, and this monomer, which is a liquid. So in principle, usually a liquid has a lower surface than a gas. Gas is more expanded, right? So the effect of pressure on a gas is the highest compared to liquid, even though both is going to affect positively to get more product. But let's say if you compare like this, you have two gas and you are increasing the pressure, it is going to be more effective compared you have one gas and one liquid with the same pressure. Make sense?
Yeah.
That's you want to?
Yeah. Thank you.
Okay. So is the slide from Sam. I think you already understand what I wanted to say. So if you have a choice of two different type of monomer, one is cheaper and which is usually give a slower reaction in room temperature, and another you have a more reactive monomer which is also expensive, but they are much faster. Now we have a choice which one to choose. Shall I go for the cheaper one or shall I go for the expensive one? Usually in the industry they find out that instead of buying the expensive monomer, if they just take the cheaper monomer and they just increase the temperature or the pressure, it is more profitable overall. It's much more cheaper to produce the product. So usually in the industry, they go for the cheaper options. They just increase the pressure and the temperature. Now you can also understand, like, even though it is cheaper, instead of buying the expensive monomer, but still you have to increase temperature and pressure, and it also requires energy. So now let's say you want to further decrease the cost. Can you tell me what is another way that you can even further decrease the cost? Let's say you take the cheaper monomer and you just apply more temperature and pressure. Of course, it takes more energy, but you want to make even cost effective. You want to make it even cheaper. In this case, you can use a catalyst. So usually, what catalysts do, they can increase the reaction rate so that you don't have to increase the temperature so much or the pressure so much, and you can have the same amount of product faster. And of course, you can save some money of it.
I feel like aren't catalysts quite expensive though? Is the price offset by the like lack of energy? Like I guess the decrease in energy usage. Is that why it's less expensive to use a catalyst?
Oh yeah, definitely. I mean, some of the catalysts, like the inorganic catalysts, they can be really, really fortune. They can cost you like a fortune. But some of the catalysts, they can be really, really cheap. Like for example, in case of polyesterification in the industry, they use a catalyst which is one of the cheapest catalysts can be possible, like sulfuric acid or like hydrochloric acid. You just have to add a few drops of it, and that is enough to start the reaction and do the catalytic activity. So it's depends, of course. I mean, you have to see all the cost of the reactant that you're using, and overall, if you see you need a catalyst which is super expensive, of course, you're not going through this process. Okay, so these are the requirements usually that you need to know for step-growth polymerizations in order to drive the reaction much more faster and getting more product. The reaction usually has to be faster. Usually the step-growth polymerization, they are much more slower. The kinetics is very slow. And now you are manipulating different conditions in order to make the reaction much more faster. You have to be completely free of any side reactions, so that, for example, you have to take a pure monomer. Whenever you're having any small molecules, you have to remove it as soon as possible, because those small molecules or those impurities, they can create side reaction, which is in a result, it can create really small oligomeric polymers, or like not a proper properties of the polymer. You have to continue the reaction until the end, because if you remember my example that I show you, you'll see that polymer in step-growth polymer you are going to have towards the end. In CGP, in chain-growth polymer, you can have a polymer even in the beginning. But in case of SGP, you can have only a high molecular polymer towards the end. So you have to continue the reaction completely towards the end. And of course, you have to take the proper stoichiometry. Stoichiometry means when you are weighing the monomer, you have to know the known concentration of the monomer, so that you know exactly, you can predict, okay, they are going to have these properties. Because in case of SGP, unlike the CGP, in case of SGP, they are going to react only A with B. Only A with B, not A, B, B, A with B. So you know, if you know the concentration of A with B, then you also know what will be the composition in the repeat unit. It's very easy to predict. And of course, you have to create the condition so that you can also have an average molecular weight, because it's much more difficult in case of SGP compared to CGP to have a narrower polymeric distribution. So these are the thing that you have to achieve, and those are the conditions that I have explained you. By manipulating those conditions, taking a pure monomer, you can achieve the reaction much more narrower polymer rate, and also without any impurities or side reactions. The high temperature is also quite important, because the high temperature will ensure that the monomer is going to only react with each other, not the side product they are going to react. So here one of the example that I just tell you, like acid catalyzed polyesterification, it is much more efficient to use a catalyst in an industry which will drive the reaction in 70 degree compared to uncatalyzed, which will take like 275 degrees centigrade. You have to also avoid the side reaction, which is also important in order to have higher molecular weight, in order to reduce the clarity, because the side reaction, they will reduce the clarity and the color purity, and it's less important for cross-linking. For example, the epoxy resin is not really important. Okay, so before I go to the Flory's equation, do you have any question here? Anything to? Yeah.
Is there reason to control the stoichiometry of the reactants so that if none of them is in too high concentration, it reacts with itself? Or what would?
So you mean that if you use too much high concentration,
Yeah.
there is a possibility the same monomer are going to react with each other?
Yeah, instead of reacting with the other monomer.
I mean, the same monomer is going to react with each other. There can be a possibility, but it's very less, because if you have a choice to react with most reactive molecule and to react with the same molecule, which is the least reactive, of course the monomer is always going to react with the most reactive choice rather than reacting with each other. But yes, of course, if you are using a super high concentration of one of the monomer, then the probability of finding that most reactive group is very low. Then they have only choice to react with each other. Then of course it will increase the probability of reacting with each other. That's a good point. Okay, so the last question that we are going to discuss is the Flory's equation to understand the kinetics of step-growth polymerization. I think this is the only thing you have to understand a little bit. The thing that I have told you before is not that brainstorming or understandable. So first of all, I'm going to start with this graph, Flory's experimental graph, which is a rate constant versus chain length. Before I start explaining, I just want to ask you, who understand this curve? You understand? Can you please explain a little bit how you are going to have, why the rate constant is decreasing with chain length?
From what I understood, we looked at, we saw that the shorter, so the longer the chain, the more valid the assumption is of having a constant, rate constant across chain length. And at smaller chain lengths, this theory is less valid, and so therefore there is a stronger change in the rate constant. Therefore, why there is a steep decrease until then getting a flatter area, flatter line from the round.
Yeah. You're right. Thank you very much. It's a little bit complicated, but yeah. Let me explain what I understand. So first of all, if I want to explain you, I'm going to explain firstly why there is a sharp decrease, because this is the only part which makes sense. So if I just come back to the previous example that I show you. So let's say you again take 8 molecule of dialcohol, 8 molecule of diacid, right? You are doing the reactions, and they are continuing the reaction. They are combining with each other, and you are making the chains. You are making the chain one by one, right? In each step. At the beginning, you have more functional group, no degree of polymerizations. More you continue the reactions, you have less and less functional group, and you have more chain length. So what is happening here, at the beginning, you have much higher possibility of finding these two functional groups of each other, because they are really small molecules, they are more flexible, and they have more functionality, so they are more probability of finding each other. More you go towards this, look here, what is happening here. This functional group has to find this one in order to create the reaction. So it's much more difficult. The probability of finding each other is way more difficult when in that long chain compared to here, number one. And number two is when you are actually doing this reaction, this polymer, they are not like straight line like this. They are entangled with each other. So it is even more harder for them to find each other. So that is the reason why there is a sharp decrease from here to here. But what is happening here is that more you go forward towards the reaction, the decrease is not that sharp anymore. The rate of decrease is also going to be slower. So in principle, if you are doing this experiment right now with the same reactant, in the same condition that Flory has been done, theoretically the curve should be something like exponential decrease. So you have to understand that when Flory did this experiment, it was like 60, 70 years ago, and whatever the instrument he has that time, and he may have some limitations of the instrument. That is why there is an abrupt change, like after 3, you completely change and is become independent of chain length. But in reality, it will be not like this. He was correct. He was not that accurate. He was correct in the sense he was able to explain that it was an asymptotic behavior. Asymptotic means what? Asymptotic is like you have a decrease towards the 0 line, exponential decay. It will go towards the 0 but never touches the 0. So that is why Flory was successful to explain the trend, but he was just not so accurate. So what is happening when you are making these chains, you have like 500 chains, and finding each other is super difficult. But finding when you have 1,000 chains is also kind of same difficult. So after a certain time, finding the functional group in a 500 chains and finding the functional group in 100 chains kind of the same. So it's become constant. So he was right, but he was just not that accurate. It's a simple way I can explain you. Like there is a lot of things was written in the book and also the other explanation. But what I understand, I think this is the simpler way. You have to just remember that the reaction rate should always decay exponentially, but it will never touch the 0. It's an asymptotic behavior, right? Okay. Any question in the curve? Any question here in this part? Right. I'm so good in explanation. No, I'm just kidding. Okay. So next I'm going to just explain you about the differential and mathematical equation. I don't know if it is really difficult for you to understand, but I'm trying to explain you a very simple way. So whenever you are writing a rate equation, let's say you start with A plus B with C, then the rate equation, usually they are the inversely proportional with the monomer that you are using. So that's why you have to put a negative sign. So ddt is a change of the concentration of A, increase of the polymer. So you are, by decreasing the concentration of the monomer, you are also increasing the concentration of the polymer. That is why they are inversely proportional, right? So this is nothing rocket science. What you have to really remember here, that A and B is just the concentration of the functional group, not the concentration of the monomer. So what I want to mean from here is that you start here with 8 molecule of dialcohol, 8 molecule of diacid. This is the concentration of the monomer, 8 molecule. But 8 molecule has 16 functional group, right? So it's completely different. So it has a double functional group. So here, if I'm talking about in the first rate equation, I'm talking about only this alcohol and this carboxylic acid group that I'm talking about. Okay, so now you have the rate equation like this. Now you have a choice. Either you can go for acid catalyzed reaction or you can go for uncatalyzed reaction. So in case of uncatalyzed reaction, usually for polyesterification, you need catalytic activity. So if you are not adding any catalyst, the monomer itself will act as a catalytic activity. How? So notice one thing here. They just add this square. Did you ask yourself why they add this square? Why they add this square is because here. So when you write the equation, you take one of the concentration of dialcohol, you take the one of the concentration of the acid. Now, in order to initiate this reaction, you need another carboxylic acid group, but you are not adding it as a catalyst. So another molecule of this carboxylic acid group is going to influence this carboxylic acid group, and then it will start the reaction. So in the actual rate equation, you have 1, 2, and 3 molecules of it. And these two are the same, that's why you are putting the power 2. And it is also experimentally verified. In the experiment, when you do this reaction without putting any catalyst, they find that the reaction is following a third order reaction. So 2 plus 1 is a third order reaction. It's experimentally verified. And this is really understandable, right? So from here, again, if you are taking the exact stoichiometry, then you know that the concentration of the carboxylic acid and the alcohol is the same, so you can just write it as a C, and then you just add up the C2 plus C1, C3, and then you have dC by dt, and then you are doing the differential calculus of it. And if you start from T0, where you have a C0, which is a known concentration, you should know when you start this reaction, you should know what is the known concentration of the monomer you are using. After time T, you have, this is unreacted monomer you have left, and then you are end up with this equation, which is just a normal differential equation here you are doing. Now, one of the things you have to remember here, if you are taking P as the extent of reactions, which is basically the number of the carboxylic acid group reacted by the number of the carboxylic acid group originally present. So this one you already know, it's a known concentration, right? This one you don't know. So now you can write this equation like this. How? C0 you already know, at T0 you have the C0. It's a known concentration, you know. This one is called number of carboxylic acid group reacted. So I can also write it in a C0 minus C, so that means the C is the unreacted one. And you are looking for actually the unreacted one, right? So if I just deduce further, then it's 1 minus C by C0, and you have to just remember P is equal to 1 minus C by C0, and that one you are going to use it to put it inside this equation. I'm going to explain you why you are doing so much differential equations and everything once you know what is the application of it. But just stay with me for the moment. Okay, so previously the P and C0, the equation that I show you, you can get this. So this is the unknown concentration that you are looking for. This is, you already know. This is already, you know from the experiment, because you are doing, let's say you are doing a titration of a kinetic experiment, you are getting some value with some particular time. This is the value actually you are getting. So this is also known, right? This is the unknown that you are looking for. So if you just put this value in the final equation, you will obtain this equation. And then you can, there is some of the steps they have to add actually, I didn't really add. So this is actually representing y is equal to mx plus c equation. If you plot this with time, you have the slope, which is this, and then they find that it's a kind of straight line, which is a normal reaction between just a esterification. So it's no difference of a normal esterification and polyesterification they find. So it is also validating the Flory's theory that after a certain time, whether you are starting a reaction with a normal ester or whether you are starting with a polymer, it doesn't depend. It doesn't really matter anymore. So that is why you are getting this linear relationship here. On the other hand, if you are doing this experiment with a catalyzed reaction, in this case, you see the previous one, you have the a to the power 2. Here you have no power because catalyzed, they doesn't take part in a rate equation, because catalyzed at the end of the day, they also become catalyzed. They doesn't take part in the rate equation. So in this case, you have, if you do the same deduction of the mathematical equation, you will end up with this, and then you just plot, and then you will have the linear equation. And experimentally, it's a second order reaction. So in case of catalyst reaction, it's a second order reaction. In case of uncatalyzed reaction, it's a third order reactions. So now you understand, okay, we do this, all these mathematical equations and everything, what is the use of it, right? You have to understand the use, otherwise you have to just remember these things. So in case of final application, if I just, yeah, I should have put this in the slide, but it's too many things to put in the slide, so that's why I didn't put it. Yeah, I don't know if you have this book, but usually the questions or people who can ask you like something, I don't know if you see it, something like this. So they will tell you the concentration, unreacted monomer that you have, with time interval. So you have the time and you have the concentration every time. And then they will ask you, okay, so this is the unreacted monomer every time interval. From here, deduce what is the reaction. It is a catalyzed reaction or it is an uncatalyzed reactions. How we can do that? Very easy. So you have to just remember this equation. Now, in the question that I show you, they tell you already about the T. So you know the time, and you know the corresponding unreacted monomer, P. So you know the P, you know the T. So once you know the P, you just convert this P to 1 by 1 minus P, right? And then you plot 1 by 1 minus P with T. And then you find whether it is showing you something like this. If it is showing you something like this, then it is a catalyzed reaction. If it is not, it is not a catalyzed reaction. Then what you gonna do? You just again do the same calculation, but in this case, you just deduce it 1 by 1 minus P whole square. And then you put the time, again you plot it. And then you see it is giving you this kind of relationship or not. And then you find it will giving you this relationship. And then you can tell, okay, so this is an uncatalyzed reaction, right? So this is the main use. I mean, if you don't know the use, there is no point of remembering this big equation, right? So you have to just remember this particular thing. This is a typical reaction equation for esterification, and you have to just remember this one, and you have to just apply the unreacted polymer with the time, and then you can find out what is the use of it. Right. Okay. Before I think I'm going to take the second hour, which I have like few questions, probably 1 or 2 questions. Before I move on to the second hour, do you have any questions so far? Really?
Could you explain again what the difference between a catalyzed and an uncatalyzed one is going to be when you plot things in the graph?
Oh, yeah, no problem. It's really no problem. Yeah. So usually, what they will tell you, they will just tell you the fraction of P. So the P is the number of unreacted monomer. How you can get it? By titration. You just titrate and you get some value, and then you get the value with time interval, right? So let's say at time 0, you have the highest number of monomer. Everything is unreacted, 100% unreacted, time 0. After time T, or like half of the time has been covered, you have like 50% of the polymer, monomer is unreacted. So you have this value in the number. And now, what you're going to do, you just take the P, you put in the Excel sheet, you take Excel, you put the P, corresponding the time, then the P, you just put it like 1 by 1 minus P, and you get the value corresponding P, just you put in Excel, just simple, normal Excel. And then you know this is the actual relationship, which is actually representing Y is equal to mx plus C. So this is the main differential equation. So you plot this as a Y axis, this one in the X axis, which is the slope C0 by T in case of catalyzed reaction. And then you plot it here, and if you get a line which is like linearly increasing, it can be only possible if the value was coming from a catalyzed reaction. Otherwise, it will never go like this. It can be like this or whatever, but it will never go like this. And now, if you see, oh, they give me this value and it's not really following this trend, then there is a second option. It may be uncatalyzed reaction. So in that case, what are you going to do? You already have the 1 by 1 minus P value, right? Then you just do one more Excel, one more column, 1 by 1 minus P whole square, and then you plot it. And then you should get a plot like this. Then you can tell, oh, this is an uncatalyzed reaction. And this is not only useful for polyesterification, for any kind of kinetic reactions. They will always give you this titration value, the P value, and the T value. And you have to just remember what is the differential equation. And you just plot it in the Excel, and just plot it. And if you plot that value, it can be different compared to the different equation. For polyesterification, this is the value. For zero order reaction can be different. For first order reaction can be different. So you just have to know the equation of it. And once you plot these two values, you have to get something like this, linearly increasing. And then you can tell, oh, this is a zero order reaction. Oh, this is a first order reaction. Is it clear?
Yeah, I have another question. question about something earlier in the lecture. It was when we were talking about step-growth polymerization of PET, and it was like reaction C, which is interfacial polymerization.
Yeah.
You said you have to do pre-treatment but post-treatment steps to deal with it, and that makes it more expensive. And you said that they were like fluffy polymer. Like, what actually is that? It's not like physically fluffy. Like, it's just like stripping stuff off it.
Yeah, so that's a good question actually. Why it is fluffy? Because of the choice of, you are actually using two different kind of solvent. So when you are actually taking this polymer out, there is a solvent inside this polymer. I think one of the best way to explain is like when you take oil and water and you just shake it very, very strongly, and you'll see they will make some kind of bubbles inside. So this is the same thing is happening in case of the polymer. So when you are taking it out, there are the chances of the two different solvents, they are still present inside the polymer, and this making this kind of spongy, fluffy structure. If it is have been in the one solvent, the possibility of making this fluffy structure is really less, because due to the presence of these two different solvent is making a kind of emulsion kind of solution, and it is present also inside the polymer and making this kind of spongy, fluffy structure. Any more question? Any question? Doesn't have to be really intelligent. I'm not intelligent. Yes?
So during the Flory experiment, when he, I guess, was the titration done as the experiment went on? Is that why it was like inaccurate? Because I feel like it's constantly changing and you're trying to titrate at certain time points. You'll get very accurate data.
Yeah, so I think in case of Flory's experiment, of course he deduced the value of P by titration, but he also did this experiment in some certain equipment. First of all, he had to do the experiment. And I guess when you are doing this experiment, in order to take this aliquot and do the titration afterwards is something quite challenging for him. So I think during the process he to be honest, he just messed up, in my opinion. And I shouldn't say a Nobel laureate, talking about Nobel laureate like that. But yeah, I think it can be kind of limitations of the instrument. But what is really important to understand from here, he may be not completely accurate to tell the graph in which way it should go, but he tell the trend actually, because the graph, if you see, it's an asymptotic graph, and he exactly say in reality also, this is also asymptotic graph. Like it is going towards the zero, but never touches zero. But in case of his graph, it was like abruptions, like dum, boom. Usually it doesn't really happen like that way. Okay, guys. If you don't have any more questions, so I'm going to take the last questions of this one, where you have to come back with some answer. Before I start, would you like to take some gap, or would you like to, or shall I just continue? Because it's not so many questions are here. It may take like 10-15 minutes. What? Shall I continue?
Yeah.
Okay. Yeah. So there is one of the sample questions is actually sent by Sam. And the question is, here you have different examples of monomer, and from here you have to just choose a combination of monomer, which will give you, first of all, a polymerizations by SGP or CGP. And then you have to find out the monomer functionality. For example, what is the functionality of the monomer, why they are going certain reactions. And you have to tell me what is the combination, the main combination of this polymer, which is going to give you a byproduct as water. Is that okay? You understand the question, right? Okay. Just take like 10-15 minutes and I'll come back. Okay, guys, shall I just start, or you need some more time? Is there somebody outside? Everybody's inside here, right? Okay. Somebody's outside? No?
Yeah, just Bill.
Okay, just give 1 or 2 minutes, maybe just.
It's okay.
Yeah. All right. Yeah, so first of all, I mean, if you want to find out which monomer combinations is going to give you a byproduct, I think the first question will be, so which technique of polymer you are going to use? So if we give you a choice of SGP or CGP, so what could be the choice that you can have a byproduct as a water? It's like, yeah, of course, SGP. And then, of course, the bifunctionality you need for SGP, which is the prerequisite for SGP to carry forward the reaction. Now, the main thing is the combination. I think you already did a little bit of thinking about it. So if you just start from the first example, and if we try to take this one and try to combine with each other and see which combination is going to give it water as a byproduct in SGP. So if I just think about the combination between 1 and 2, do you think it's a feasible reaction in SGP? Does it give you a water? Yeah. So this is one of the answer. About 1 and 3, does it give you any reaction at all? What reaction it would be? SGP, right? Yeah. But what would be the byproduct in this case? Exactly. So, I mean, before I continue, just to tell you one thing here. Usually when people do a combination of SGP between dialcohol and diacyl chloride, of course you have a byproduct HCl, they add a little bit of base. Do you know why? Because in order to neutralize that excess acid. So, as I told you in the last atelier principle, you can also drive the equilibrium towards the product by removing the product or by neutralizing the product. So if you can neutralize that byproduct HCl with a base, you can also have more product much faster. So this is not only for SGP, but also any kind of reaction where you're having acid as a byproduct, you just add a little bit of base in order to increase the rate of the reaction. Or if you are having byproduct as a base, you add a little bit of acid in the reaction. What about a combination between 1 and 4? Does it give you water as a byproduct? Yeah, so that is one of the answer. Between 1 and 4, does it really go SGP? No, because this styrene is actually suitable for CGP. 1 and 6, it's the same. 1 and 7. It's the same. 1 and 8, it doesn't have any reacting side at all. What about 1 and 9? Yeah? It will give you a water as a byproduct. Okay. So if I just take now the combination between 2, they already give you a byproduct as water. What about the combination 2 and 3? They're not going to react with each other because both of them are kind of the similar electron withdrawing group. So remember, you need a combination of 1 electron withdrawing, 1 electron donating. So here in this case, both of them are electron withdrawing, so they're not going to react.
Wait, did you say 1 and 9 would react or would not?
1 and 9?
Yeah.
Yeah, definitely, yes.
But then they also both electron withdrawing.
Yeah, that's true. They are electron withdrawing, but there is a difference in electron withdrawing group. Like this one is more reactive, this one is less reactive. So even though they are kind of the same, but you need to put more energy in order to drive the reaction. I'm going to check the answer. You are actually right. I'm going to come back to this reaction. Maybe I'm wrong, you know. Okay. What about combination 2 and 4? No, of course not, they're the same. It will also doesn't go with this one, doesn't go with this one, this one, this one. What about 2 and 9? Yeah, so this is another answer. The 2 and 9 is going to give you a product. Yeah, so with 3 and 4 is the same. They're not going to react. With 3, it can react with 9. Does it react? Yeah, it will react, But in this case, you have the small molecule as a HCl acid. What about the combination between 4 and 9? They are going to react, and they're also going to give you water as a small molecules. And what else is already left behind? Yeah. So I think almost all the combination is done. And of course, you are right. It will not go. I was right. Sorry for that. It will not going to react with this one and this one. I thought it's just an acid, but it's not acid. It's alcohol. They're the same electron donating group, and they're not going to react with each other. Yeah. So I think these are the combinations you have. Yeah. So do you have any question here? It's okay. Yeah. Okay. With that, I think I'm going to wrap up for today. I think the weather is really great. Thank you very much for again being in my class. It was really, really great to talk with you guys. Yeah, and the next class, I'm going to tell you if I'm going to take the class. If not, then Sam is going to take the class. So yeah, with that, just enjoy the rest of the day. If you have any question, just ask me or ask Sam. Right? Okay, great.